Welcome to your last and final video of the flipped classroom on 7.7 writing exponential functions. It's pretty typical in this book that one of the last sections, besides trying to solve equations like we did in 7.6, is what if we try and apply this to real life and I give you real-time data, or if I give you some sort of data about a specific situation that I think looks exponential. Is there a way to take that data and try and fit it into some kind of model so that I can predict what's going to happen in the future? And that's what 7.7 is all about. So remember, the most basic form of an exponential function is y equals ab to the x, where a and b are just numbers and y and x are the variables of the actual function itself. What if you have data, or I give you points that fit an exponential model? How do you write an exponential function when given data sets or coordinate pairs? So basically, we're going to reverse. Pretty much this entire chapter, I've given you the model, and then you've generated points to go ahead and graph or find answers or whatever you're doing. But what if I give you the data and ask you to actually give the model? We've done this before, okay? And specifically, the reason we've done this before is think back to quadratics. When we had quadratics and I said, okay, try and fit a model that passes through something like -1, 4, and 3, 10, and 6, 12. Now I'm completely making up those points, but what we had to do is we had to use that generic form, the standard form of a quadratic, y equals ax squared plus bx plus c, and we had to plug in y and the x for each one of those points. And when we did that, then we created a system of equations. Well, we're going to do something similar in this one, but it's not going to be nearly as complicated as a quadratic was. So let's take a peek at one. It says, write the exponential function whose function passes through the points 110 and 480. Now, again, remember that we have the most generic form of the equation, y equals ab to the x. Okay, so if I take that first point, 110, obviously I know that 1 is the x and the 10 is the y. So I'm going to plug that into the generic form. So if I take that generic form, it really means it's 10 equals, because y is 10, a times b, really raised to the x or raised to the first power. Similarly, so obviously that condenses down to a times b. Similarly, if I do that same thing for 4, 80, my x is 4, my y is 80, plug it into that generic form, so I have 80 equals a times b to the fourth power. So that breaks down into 80 equals ab to the fourth. Now realistically, I have two forms here. I have 10 equals ab, and I have 80 equals ab to the fourth. Given the fact that I have two variables in two equations, I should be able to solve for one variable in one equation and use that substitution method to go ahead and plug it into the other. So for sake of ease, I'm going to take this one and I'm going to solve for one of the variables. Doesn't make any difference which one. I'm going to choose this to go ahead and solve for a. If I try and solve for a, I think I need to divide by b on both sides. The b and b cancel out, so I think I now have 10 over b is equal to a. So if that's the case, I'm going to take what a is equal to, and a is equal to 10 over b, and I'm going to plug it in wherever I see an a in that second equation. Okay, so now if I come up over here and I go ahead and try and solve this, okay, I'm going to take that second equation. It used to be 80 equals ab to the fourth. But now I know a can be represented as 10 over b from the first one. So I'm going to say 80 equals no longer a. A has been substituted out for 10 over b, all to the b to the fourth. Now I can see here this is really b over 1, so if I want to simplify that, I really can say, hey, well, that's 80 equals 10b to the fourth all over b. And that's really b to the first power, and we know using our exponent rules that b to the fourth divided by b to the first, that's a base divided by a base. Therefore, I can do 4 minus 1, which obviously gives me 3. So now I have 80 equals 10b to the third. Now simply solve for b. Divide by 10 on both sides, and that means I have 8 is equal to b to the third, and I want to get rid of the third, so I'm going to do the cubed root on both sides. Cube and cube cancel out, So I have b is equal to the cube root of 8, which we know to be 2. Now that's pretty nice, because now if I have b, I can go back to my original equations, the one I have squared off in black on the left side, either this one right here or this one right here, to go ahead and solve for the other variable. Obviously it looks like the first one's a little bit easier, so if I plug in, and I'm going to try and find a little bit of space here, maybe I'll go ahead and just erase this work over here. If I go ahead and plug b back in, so I'll keep this here so remember what our variable was. If I take that first equation, 10 is equal to a times b. I now know b is 2, so 10 is equal to a times 2. Obviously divide by 2 on both sides, therefore I get a is equal to 5. Now, I have both a and b, so now I could be able to write my final exponential function. I should be able to say my final exponential equation is, or function is, y equals a, which is 5, times b, which is 2, all raised to the x. I guarantee you, if you took time to graph this function, I know it passed through 110 as well as 480. And as a matter of fact, let's go ahead and do that. I'm going to grab my calculator, bring it all over here. Actually, I'll bring it right here for us. And my function was, if I go ahead and graph it, I know my function was 5 times 2 raised to the x. So if I graph that, I'm going to go ahead and do zoom 6 to make sure I'm on my standard window. Okay, and I have something that looks like this. Now, I think if I go ahead and hit trace and hit 1, it better be at 10, which sure enough it is. And similarly, if I say my input is 4, x is 4, I better get an output of 80, and sure enough it is. So that function right there describes the one exponential that actually passes through both of those points simultaneously. Okay, go ahead, let's try it one more. It says 1, 6, and 324. I want to write an exponential function that passes through it. So let's do the same thing one more time. I have the point 1, 6. I'm going to take the most generic form. So I have my generic form again is y equals ab to the x. Okay, plug in the points that I have. So now I have 6 is equal to ab to the first power, which I think ends up to be 6 equals a times b. That's one of my equations. And similarly for 324, I'm going to plug in what I know. 24 is equal to ab to the third power. That's my second equation. And then again, I'm going to take one of them, solve for one of the variables, and then go ahead and plug it in or substitute into the other function. Okay, again, I think this one's probably the easiest. If I solve for a, I'm going to go ahead and divide by b each, so I think I get 6 divided by b is equal to a. And I know I'm going to take what a is equal to and go ahead and plug it in wherever I see an a, which is right here. Okay, so now let's plug it in. 24 equals, it used to be a, now it's going to be swapped out for 6 over b times b cubed. Okay, if that's already over 1, I can multiply fractions, so I really have 24 equals 6b cubed all over b to the first power. Base divided by base, b divided by b. I can subtract the exponent, so 3 minus 1. So I think I get, I'll go ahead and move this for us. I think I get 24 is equal to 6b squared. I'll bring it up over here so I can finish it. If I go ahead and divide by 6 on both sides, so go ahead and simplify my terms. 24 divided by 6 is 4 is equal to b squared. And then take the square root of both sides, and I get b is equal to 2. Once I have that, I can now go back to either one of those initial equations, this one right here or this one right here, plug b back in, and you should be able to solve for a. I think the first one's the easiest, so I'm going to take that. 6 equals ab. I now know what b is. 6 equals a times b, which is now 2. And divide by 2 on both sides, so I get a is equal to 3. If that's the case, I think now I have both the actual numbers that I need to go ahead and write my final function, and my final function should look like y equals a, which is 3, times b, which is 2, all raised to the x power. Again, keep that in mind. Let's see if we can graph it one more time to make sure we're actually right. I'll come back to here, go back to y equals, clear out the screen, and my function was 3 times 2 to the x. So I'm going to type it in, 3 times 2 all raised to the x. And when I graph it, I have my graph there. Now let's check our work. When I plug in 1, when I trace at 1, I should get out 6, which I do. And when I trace at 3, I should get 24, which I do. Okay, very, very slick. The only last thing I'm going to show you is if I were to go ahead and try and do this in my calculator to verify I'm actually doing it right and I didn't want to have to graph it, okay, we should have an idea of how to do it with our stat plot. If I go to stat right here, I can go into edit like we've done before, and I have other stuff in here, so I'm going to go up to L2, clear that out. Okay, go over here, go to L1, clear it out. Okay, always get a nice new fresh window. And plug in your data. L1 is going to be your x coordinates and L2 is going to be your y coordinates. So I think I have 1 and 3 for my x coordinates in this problem. And then the corresponding y values are 6 with the 1 and 24 for the 3. So now I can go back to stat. I should be able to go to calculate. And if I keep going down, we've done a lot of these already, but we should go down to exponential regression, which looks like it's number 0. If I hit enter, and I hit enter one more time, I have y equals ab to the x. There's my a value of 3 and my b value of 2, which is exactly the same that we got both graphically as well as algebraically. So now you really have 3 different ways to go ahead and write your function. That's all I got for you today. I'll see you tomorrow. Thanks for being a part of my flipped classroom.